We are the Safe AI group from the University of Bristol. In the previous video, we have illustrated how to use the item response theory to benchmark machine learning models and datasets. In this video, we will demonstrate how to use the framework of IRT to accelerate the overall efficiency of model benchmarking. Back to our example of examination. We want to estimate the goodness of a student by assigning a set of exam questions. While we should know the student better by giving more questions, it is unlikely that anyone will simply sit there and answer questions all day. Here, one solution would be to select a subset of questions instead. Although this selection can be performed by either the examiner or the student, both sides have limitations. The examiner can only select a fixed set of questions. Therefore, the question set cannot be tailored for every student. On the other hand, the students will try to select the questions that optimize their scores. The framework of adaptive testing provides an alternative solution by selecting the questions on the go. The idea is to dynamically adjust the question difficulties to estimate the student ability fast and accurate. For example, if the student failed to answer a specific question, it would make more sense to next provide a more straightforward question. If the student has successfully answered a few consecutively, it is probably time to ask a more challenging question. Now let us move back to the context of machine learning benchmarks. We would like to try the candidate model with all related datasets to pay for our lunch in the ideal scenario of unlimited computational power. However, since we don't have such luxury, we can use the adaptive testing framework to reduce the testing costs while still maintaining a reasonable estimate of our model's goodness. The intuition follows the examination example. Given a candidate model to be tested, you probably don't want to start with the CIFAR 100 dataset, as most models might end up with mediocre performance, and we don't understand the model much. You also don't want to start with the mushroom dataset, as most models will end up with high accuracy regardless of their learning ability. The adaptive testing framework, therefore, aims to find a middle ground. You start by guessing a reasonable ability of the candidate model, which could be the median of all existing models. With this initial guess, you can start checking every dataset under consideration. Intuitively, you don't want to find datasets that agree with your current guess. Spending experiments on such datasets won't change the estimated ability much. Multiple methods have been proposed to perform such a selection. One of the most adopted is the Fisher information. We can loosely think that the Fisher information considers the discrimination of the dataset, given the current model ability. If the gradient has a higher norm, the curve changes more rapidly around the current model ability. Running experiments with such datasets will more likely either increase or lower down the ability value. Here we show some results of the Fisher information with the logistic IRT model. We trained the IRT model on the accuracy measures collected from 16 different fully connected networks on 162 datasets. And we want to know, what is the position of a default sklearn random forest on these datasets among the deep networks? We can see the adaptive testing method selects the CIFAR 10 dataset for the first test. As the response curve indicates, the chosen dataset follows our idea on the Fisher information. The dataset has an apparent discrimination power given the curve's rising trend, distinguishing every model distinctively. The random forest then receives an accuracy of about 0.45 on this dataset. And we can update the estimated ability to match this information. The testing then moves to the MNIST dataset and then the CIFAT 100 datasets. All the first 3 selections are well-known computer vision benchmark datasets, and it makes sense as we are comparing the candidate model to a bunch of neural networks. The adaptive testing will then repeat this procedure until a given stopping condition is satisfied. For illustration, we allow the testing to run through the entire dataset collection. We can see the cloud dataset is left to the last few in the testing sequence, and the dataset basically gives a flat line and not telling much information on the model goodness. While this video only covers a brief introduction of the adaptive testing idea, please check our software GitHub for more information and examples. Thanks for watching.